Kocher from the National Lab of the Rockies, and Jordan is currently a postdoctoral fellow at the National Lab of the Rockies. He's currently serving as the co-chair of the Buildings Technical Committee for the Energy Sustainability Conference, and his presentation is Pathways for Efficient and Inexpensive Cooling from Residential Buildings to Data Centers. Welcome.
Thank you, Zulong, for the introduction. Thank you all for being here to attend my talk. So I'll be presenting today on some analyses that we've done in NLR on the thermodynamic efficiency and cost effectiveness of different cooling system architectures, as well as the different exergy inputs that we can use for cooling systems from the residential scale all the way up to large building data center scale. So I want to start off by saying that what I'm going to be presenting today is work that we've done for this publication that was recently submitted to Joule. So hopefully, if there's anything that I don't cover today, you can take a look at that paper soon once it's published. And in this paper, we started off by looking at the function of air conditioning. So very fundamentally, thermodynamically, what is it that air conditioning systems do? And really that function is twofold. So the first is kind of the obvious one, and that's to sensibly cool your air, so to lower the temperature of the air to a comfortable value within your building. But the other part of it is dehumidification, also known as latent cooling. And from a thermodynamic standpoint, that is a separations process. So you start with your humid inlet air, and you're trying to separate that into dry air and then exhaust water, and that could be liquid or vapor, depending on your system. So you've got a cooling process and a separations process in every air conditioner for the most part that you are going to use. And so this over here is a simple schematic of a conventional air conditioner. And it's really convenient because it does both of those things, the cooling and the separation at the same time. So we've got this vapor compression cycle where we've got a compressor, condenser where we reject our heat, an expansion valve, and then an evaporator. And at that evaporator, you've got cold refrigerant, which is cooling off the air that you're going to provide to your building, but it's actually overcooling it to a lower temperature than you want, just in terms of thermal comfort, for the sake of condensing that moisture out of the air to get your separation or your dehumidification. So it's not very efficient because you're overcooling your air, but it is really convenient, and that's why almost every air conditioner in the world uses this system architecture. So when we were looking at this study, we wanted to see, okay, well, where is the room for improvement? How do we actually improve our air conditioners? So one question was, can we improve the vapor compression cycle itself? And what we found is that the vapor compression cycle is actually really efficient already at producing hot and cold refrigerant. So within this system boundary, there's not a ton of room for improvement, even though there are a lot of researchers that are looking at non-vapor compression technologies to make cold and hot. So caloric refrigeration is a way of doing that. But we found that it's already very well optimized within the system boundary. So where a lot of the inefficiency is happening is outside of that system boundary. So when you're actually trying to cool the air and reject heat, that's where you introduce a lot of your inefficiency. So our current processes use these very efficient components, but in a very unfavorable or inefficient way. So we're wasting a lot of energy when we reject that heat, and then again with that overcooling and that lower evaporator temperature, we're wasting a lot of energy. So we started thinking, okay, well, how do we make air conditioning more efficient? And so these are some of the components that you can use to make an air conditioner. You can combine these in different ways. And in general, this is how we're moving towards more efficient air conditioning. So on the latent side, so that's dehumidification, there have been systems that have been proposed in literature that use any number of combinations of these different components. So water vapor compressors, water selective membranes that allow water vapor to pass through but not air, desiccants, and then the vapor compression cycle itself, either as a heat pump or a refrigeration cycle. Those have been proposed as components for the latent portion. And then for the sensible portion, once again, we have the vapor compression cycle, just to sensibly cool the air. Or, we have something like dew point indirect evaporative cooling. So this uses water as the input instead of electricity, and it cools off the air without humidifying it. So these are some of the different system components that we looked at. And we were trying to figure out, well, what's the optimal way to combine these in a system that can efficiently cool anything from a residential building up to a very large scale data center type building. So this is our thermodynamic analysis of that conventional air conditioning system, so just vapor compression, none of those other extra components. and it's got that cold surface condensation, which, as I said before, is very inefficient. And so these are the exergetic efficiencies that we're seeing for this conventional air conditioner system architecture. Okay, so exergy, if you're not familiar with that term, you can think of that as thermodynamic potential or useful energy. So when we say exergetic efficiency, we're just saying how efficient are we compared to the thermodynamic limit. So we can see that conventional air conditioner, is as high as 20% exergetically efficient, but in some cases when we're really far at these unfavorable conditions, we're really low efficiencies, around 1 or 2% exergetic efficiency. So very low efficiencies with a conventional air conditioner. So how do we improve that? As I said before, the way to improve that is not by improving the vapor compression cycle itself. This is the exergetic efficiency of just the vapor compression cycle at producing hot and cold refrigerant, and that is actually around 70% exergetic efficiency. So that's not where we're losing our exergy, that's not where we're introducing inefficiency. We're doing it elsewhere, and so improving that cycle, replacing it with something like caloric refrigeration, that's not the way to go. So this is one system that would improve the exergetic efficiency. So this is a desiccant system that is regenerated by a heat pump. So how this works is we've got a vapor compression heat pump here, and it's producing cooling at the evaporator, and that cools off our liquid desiccant. And then our liquid desiccant is both sensibly cooling and absorbing moisture from our supply air. And then on the other side, we've got the condenser of our vapor compression cycle, and we're heating up our liquid desiccant to regenerate it to get that moisture out, exhaust it to the outdoor air so that we can keep using our liquid desiccant. So what's nice about this is that it reduces the refrigerant temperature lift, and so that improves the efficiency of our system. The way that it does that is we don't have to cool all the way to the dew point to condense moisture out of the air. We're using the liquid desiccant to absorb that moisture, and so we're able to operate with a smaller refrigerant lift and thus improve efficiency. And you can see over here, our exergetic efficiency has gone up by as much as 50% compared to the conventional air conditioner. So this is a much more efficient system architecture. But fundamentally, this is still providing cooling and dehumidification at the same time. So another system architecture that we can look at is one that would separate that latent load and the sensible load. So in this system, we're dehumidifying the air first, and then we're sensibly cooling. So what we do for the dehumidification side is we send that air over a water vapor selective membrane. Okay, so this is a membrane that allows water vapor through, but it allows very little air to pass through. So over here we've got mostly water vapor, and then we're condensing that water vapor with a vapor compression cycle. Okay, and so we've got this condensate that we're getting as a byproduct, but the main thing here is that we're removing that moisture from that indoor air to provide our dehumidification. And so we could use another vapor compression cycle to then cool off our air for the sensible cooling, but we're producing this condensate over here, so what if we reuse that to improve our efficiency? So we looked at modeling an indirect dew point evaporative cooler over here. So we take this condensate, we use that as our water supply for the evaporative cooler, and the way that it works is the air goes through, it's pre-cooled through a heat exchanger, and then a portion of it goes back through and evaporates water on the other side to produce cooling, and is then exhausted as humid air. But then a portion of that initial pre-cooled air is just then taken off as our supply air to our building. So we're able to cool our air without directly humidifying it. So a normal evaporative cooler is called a swamp cooler because it's making the air more humid. Here we do it without making the air humid. And so that's a benefit of this dew point indirect evaporative cooler. And so you can see that this system is, again, more efficient than a conventional air conditioner. And it's actually more efficient than the desiccant system at these higher temperature lifts that we're trying to achieve. So basically both of these systems that I've showed you that are an improvement could be used in different niches. So very high temperature lift, you'd want to use this system that I'm showing here. Smaller temperature lifts, you'd want to use the desiccant system that I showed on the previous slide. So by separating the sensible and latent load, we again reduce that required refrigerant lift within our vapor compression cycle. So that's just a better way to use vapor compression. So the cycle itself is efficient, and now we're using it in a more efficient process than a conventional air conditioner. And that dew point indirect evaporative cooling itself has a very high exergetic efficiency, leading to this system architecture being favorable. So the other thing that we looked at was, okay, what if we were using a different exergy source than electricity, right? So vapor compression runs on electricity. That's what almost all air conditioners use as their exergy input. But an evaporative cooler uses water as the input. So we wanted to compare the cost of those two different exergy sources. So what I'm plotting here is the cost per unit exergy of both liquid water and electricity. So these blue dots, that's the cost per unit exergy of liquid water, and these yellow dots, that's the cost per unit exergy of electricity. So what you can see is that in many locations, water is a much cheaper exergy source than electricity. So even if the exergetic efficiency is comparable, using water can lead to a cheaper system because it itself is cheaper to input than electricity. So that's the first finding that we had, and then we wanted to see, okay, in which locations would it make the most sense to use evaporative cooling and get the benefits of that cheap exergy source of water. So we've plotted here a regime map where we've got the liquid water exergy on the x-axis, and then the cost difference between electricity and liquid water on the y-axis. And so as you move up, this means that water is more cheap than electricity. And then as you move over to the right, these are drier locations where water is more exergy dense and it can do more useful cooling. And so really it's over here where water has the most benefit as an exergy source compared to electricity. So obviously places that are dry like Phoenix or Riyadh, those are very exergy dense areas for liquid water, and so it makes sense to use water for cooling there. But then also places like New York, which aren't particularly dry, but have really expensive electricity, those would also be good places to use water as an exergy source. And what this shows is that you don't have to use water as your only exergy source, but shifting some of your exergy input to water could be useful. So maybe you still use some electricity for dehumidification, but then you use some water input for that evaporative cooling, and that could be a more cost-effective system architecture. So I want to compare a few different systems here and show you, using this exergetic framework, why so many data centers in particular like to use water for cooling. So right here, I've modeled just a simple vapor compression cycle that is dry cooled, so it's an air-cooled condenser. And I've modeled 20 kilowatt hours of exergy for cooling, and based on the ambient conditions, so this is a dry climate, and then the air that we're trying to cool, I found that this particular vapor compression cycle would be 20% exergetically efficient when you're using an air-cooled condenser. So you'd need 100 kilowatt hours of exergy, and then just based on the cost of electricity, I said, okay, so that's 75 cents for the exergy input in this case. So what if we instead use an evaporative cooler to produce water at the wet bulb temperature, and now we're ejecting heat to that wet bulb instead of the dry bulb temperature. So our COP for our vapor compression cycle goes up in that case. You can see that the overall exergetic efficiency goes down. So this is slightly less efficient than that previous system I showed, but it costs less to operate, even though it's less efficient. And that's just because we've now switched some of our exergy input to this water in the evaporative cooler, and less of our exergy input is coming as electricity. And as I discussed on the previous slide, water is usually a cheaper exergy source than electricity. So even though the system's slightly less efficient, it's a lot cheaper to operate because we're using that cheaper exergy source. So what I'm showing here is kind of like the ideal system that if we could, it would be really great to move to, where maybe we need to use desalination because fresh water is not available everywhere. And we use that desalination to produce some fresh water, and then we use that fresh water in an indirect evaporative cooler as opposed to that simple wet bulb evaporative cooler that I showed in the previous system. And this system here is actually pretty efficient. So when you include both the desalination system and the indirect evaporative cooler, it would have a 20% exergetic efficiency. So that's the same as the vapor compression system by itself. But the really big thing here is that we've switched most of our exergy input from electricity to the exergy within seawater. So seawater has a lot of exergy in it compared to ambient air. And so now we're getting most of our exergy input from that seawater, and very little comes from electricity. So to run this system, you're just paying for the electricity, And so that leads to a really low cost to operate this system. Now, of course, there will be CapEx here associated with the desalination system, and so that has to be considered. But from an OpEx perspective, this could be really favorable compared to the other two systems, mostly because we're sourcing our Exergy from that seawater. So really quick before I conclude, I want to talk about a simple case study. So what I did is I looked at the weather data for LA last week. So Thursday was a pretty warm day in LA. The dry bulb was 91 degrees Fahrenheit, the dew point was 65. And during the hottest part of the day, AC accounts for about 40 to 50% of grid demand in Los Angeles, just based on prior data. So if we assume that the grid demand on that day was about 5.5 gigawatts, which is typical for such a summer day, that means that AC would account for about 2.5 gigawatts of electricity consumption within the city of Los Angeles. So if we assume that our current building stock within the city of LA has an average COP of about 3, then that would mean that the cooling demand at 3 p.m. last Thursday was about 7.5 gigawatts thermal of cooling. So that's what the city of LA needed during that hour. So next we can look at how the electricity demand, so how much that grid strain due to air conditioning would look if we improved our air conditioning systems from this kind of average COP of 3. So again, just to start off, 7.5 gigawatts, and then I'll talk about the current AC stock. If we implemented higher efficiency but still dry cooled vapor compression, and then if we instead switch to that dew point evaporative cooled. So right now, with that current AC stock, we're looking at about 2.5 gigawatts of strain on LA's electric grid due to air conditioning. But if we switch to more efficient, more modern vapor compression systems, so we modeled this at the National Lab of the Rockies, so we have a model for existing kind of high efficiency vapor compression systems. The COP during that hour last Thursday would have been 5.4, so a good bit higher than that value of 3. And in that case, we would only need 1.4 gigawatts of electricity to source the air conditioning for the city of LA. But now let's look at this case where we're using desalination to produce water to then use in evaporative cooling. So we've got our desalination system. We would only need 0.04 gigawatts of electricity to provide enough fresh water to then reject all of our condenser heat to that evaporatively cooled water. And then again, the dew point last Thursday was 65F, so way lower than that 91F dry bulb. So now our vapor compression COP goes up to a value of 10.9, so way more efficient. And so our vapor compression energy input goes down to 0.7 gigawatts. So we're overall able to significantly reduce the strain that air conditioning places on the electric grid by using this combination of desalination and vapor compression. And the benefit here is that we're not actually stressing the water situation within LA any more than it currently is because we're sourcing all of that water with desalination. So just to quickly conclude, conventional vapor compression is inefficient, but it is very convenient. So that's why we use it. Dehumidification is currently performed with excessive refrigerant temperature lift, which is why we have all these losses for dehumidification specifically. Systems that reduce that refrigerant lift through some means, whether that's separate, sensible, and latent, or we're using desiccants, that improves efficiency. When available, water is often a low-cost Exergy source for cooling. Shifting that system's Exergy input to a cheaper source like water reduces the cost to operate it. And we know that water is an effective source of cooling, and it can be an effective source even in locations that are water stressed if you use it with desalination. So with that, I'll conclude my presentation, and I'm happy to take any questions.